Hello and welcome to the second part on our videos on lithium batteries. And in this video we will talk about the electrolyte that is in between the two electrodes. So electrolytes, they can be liquid, solid or polymer. Lithium systems can therefore also be categorized by the electrolyte used. For example, lithium-ion polymer cells or lithium-ion cells with liquid electrolyte. Liquid electrolytes are typically organic solvents with a conducting salt dissolved in it. Because lithium is a reducing agent that reduces hydrogen ions to hydrogen, aqueous electrolytes cannot be used. The electrolyte solution must be a product, for example electrolytes that do not split off protons. In place of organic solvents, ionic liquids also can be used. These liquids are salts that remain liquid even at room temperature. In polymer electrolytes, the conducting salt is aggregated in macromolecules or embedded in a polymer matrix. Liquid electrolytes can be also embedded. Since polymer is an electrical insulator as well as dimensionally stable, a separator is not required. Because of its high internal resistance, poor in ion conductivity, it only allows low discharging currents compared to liquid electrolytes. Gel electrolytes can be used at room temperature, and solid electrolytes can be used at temperatures of around up to 60 degrees. Some polymers such as polyvinylidene fluoride, polyacrylene triol and polyethylene glycol are described as examples. Frequently, the ion conductivity of polymer electrolyte is inadequate at room temperature. Alternative solid electrolytes are, for example, ion conducting glasses. In general, various electrolytes can also be mixed to combine the individual materials' different benefits. Because of their practical relevance, only the liquid electrolytes are discussed in what follows now. The electrolyte transports the lithium ions. So conducting salts dissolve easily when the solvent has a high dielectric constant epsilon and the solvents are dipolar. In addition, a low grid energy between the conducting salts cation and anion facilitates its dissociation. In this table we have several solvents listed with their physical parameters, and with its high dielectric constant of approximately 90, ethylene carbonate EC is one example of a suitable solvent with good solubility for conducting salts. When the lithium ions can move easily in the solvent and electrostatic interaction with its anion is low, high ion mobility results. This can be easily demonstrated by observing the movement of lithium ions in the electrolyte solution when an external electrical field E is applied. The electrical power, together with a frictional force proportional to the speed v in the opposite direction, both act on the ions that you can also see in the Stokes drag. In steady state, a balance of the forces results that we see in this equation. And in this equation, the Q is the ion's electric charge, the eta is the dynamic viscosity of the electrolyte solution, and R is the radius of a particle. In addition, the mobility U of the ions is determined by this equation, and the ion mobility of lithium ions is therefore high when the dynamic viscosity of the electrolyte solution is low. The viscosity of liquids in relation to temperature can be approximated using this formula with A and B as constants, where both A and B are bigger than 0. As the temperature T increases, viscosity decreases, facilitating ion mobility. In comparison to other solvents such as dimethyl carbonate DMC, diethyl carbonate DEC and ethylmethylene carbonate EMC, the ethylene carbonate has a comparably high viscosity and so also a low ion mobility. To obtain a high dielectric constant together with low viscosity, organic solvent mixes are used. The mixing ratios are determined by the application area. The use of organic electrolytes is determined by the lower temperature limit, solidification, and the upper temperature limit is the vaporization or decomposition limit. Since electrolyte solution melting and solidification temperatures depend on the mixing ratio, these must be determined separately or looked up in phase diagrams. For example, an EC-based electrolyte with melting temperature of around 36.4 degrees, solid at room temperature, can only be used in combination with a solvent with a lower melting point, such as, for example, DEC or EMC at temperatures above around minus 20 degrees. The upper temperature limit of the lithium-ion cells is in practice not determined by the solvent mixture's evaporation point. This is preliminarily determined by the conducting salt or other components. So, looking at those conducting salts. Conducting salts with good solubility and electrochemical stability are, for example, lithium perchloride, lithium hexafluoarsenate, lithium hexafluorophosphate. Their ion conductivities are in the range of a few millisiemens per centimeters and depend on the solvent used with the salt. Gradually increasing the conducting salt concentration, starting at a very low concentration, also increases the conductivity. This is because the increased numbers of dissociated ions in the electrolyte solution results in an increased number of charge carriers. But if the concentration is increased even further, the conductivity falls. At higher concentrations, interaction among the ions increases, leading to reduced conductivity. Conducting salt concentrations are typically around 1 mole per liter. Coming to the electrochemical stability window. To determine the electrochemical stability of an electrolyte, measurements are typically compared with those taken from an inert reference electrode. To determine the electrochemical stability of an electrolyte more exactly or more precisely for a particular application, these measurements must be compared with those taken from the surfaces of the active materials used with the electrolyte in the lithium cell. The ideal electrolyte would be electrochemically stable in a range of around from 0 to 5 volts, so in a range covering all relevant electrode materials. Organic solvents are stable within a range of approximately 1 to 4.5 volts, and new electrolytes are currently being developed with higher conductivities that remain electrochemically stable even at higher voltages. Here we again see the graph we have seen in the first video, where we have this electrochemical stability window. As a result, what is determined, or what is termed the electrochemical voltage window, is limited by the electrolyte's oxidation potential and the reduction potential. Since they limit the cell voltage, they also limit the areas of application. The oxidation potential of around 4.5 volts is linked to the highest occupied molecular orbital, and the reduction potential of around 1 volt is linked to the lowest unoccupied molecular orbital. If the redox potentials of the active materials fall within the electrochemical voltage window and the cell is used within this window, then irreversible decomposition of the electrolyte for reduction of oxidation is largely avoided. Because of the strongly reductive or oxidative effects of the active materials, in reality the phases thermodynamic stability when side by side is not preliminarily due to the electrolyte stability when in contact with the electrodes. it is rather due to chemical passivation of the active material surfaces. If carbon electrodes are used as negative electrodes, then the redox potential lies outside the electrochemical stability window of the organic solvent, around 1 to 4.5 volts. As a result, the electrolyte is reduced at a negative electrode because of its low potential. With the solvent EC, this occurs at a potential of around 0.9 volts. The electrolyte partially decomposes each time the cell is charged, or generally whenever the electrode potential is outside the stability window. Over a long time, this results in large losses in capacity. The decomposition products of some solvents, for example EC, from a stable lithium-ion conducting passivation layer on the anode surface, which permits reversible operation of lithium-ion cells. This layer formed is termed a solid electrolyte interface, SEI. The SEI layer is permeable only by lithium ions, and this intermediate layer protects the negative electrode from intercalation by other solvated lithium ions and the electrolyte from further decomposition. It is created during its first charge. In contrast, the solvent propylene carbonate decomposes at a low electrolyte potential, around 0.5 volts. Its layer formation behavior is therefore inferior. Besides providing protection, the intermediate layer also increases ion conduction resistance. If active material redox potentials within the electrochemical stability window are used for the negative electrodes, then no SEI layer is formed. For example, with the lithium titanate cell with 1.55 volts. When lithium titanate is used for the negative electrode, the higher redox potential at 1.55 volt results in a lower cell voltage. Another result is reduced energy density. It is necessary therefore to strike a balance between higher energy density or stability, which induces a longer lifetime, and lower internal resistance of the negative electrode. This means that these materials have the advantage of increasing the cell service life, but the disadvantage of reducing the usable specific energy density. And in the next video, we will see that anode and cathode don't like each other, so they need to be separated. And on that, we will have a closer look in the next video. Thank you very much.